What I had in mind, the bicycle wheel was an example of a rigid object. What is a rigid object? A rigid object is one, if you think about it, which has the property that the distance between any 2 points on it is fixed. So it can move around like this, or it can rotate, or oscillate, whatever. But it remains intact as a rigid object, okay? A non-rigid object is one where the distances between various parts of it can change with time. For example, and this is a classic example, an ice skater who moves her arms down to her side. You know what happens when an ice skater is spinning with arms outstretched and then pulls the arms in, they speed up. That was a violation offhand. Looks like a violation of what I said was Newton's first law of rotational mechanics. That something that's spinning keeps on spinning with the same velocity, same angular velocity, unless acted on by some force or by some torque. That was an example where it didn't keep going with constant angular velocity. On the contrary, when she pulled her arms down, she spun faster. She was not a rigid object. The distance between her hands, for instance, and her legs changed when she pulled them in, so that was not a rigid object. But I should absolutely have said that. For the moment, I'm talking about the rotational mechanics of a rigid object. Next week, we'll talk about how the theory extends to non-rigid objects, like swarms of bees or something, where obviously the distance between any two of them is not fixed in time. Is there any question about what I mean by a rigid object, then? It's exactly what the word sounds like. Okay, rotational mechanics of a rigid object. The basic theorem, the basic law applied to this is what I call Newton's second law, in quotation marks, but the rotational analog to the true Newton's second law. It says tau, the torque acting on an object, is equal to I, its rotational inertia, times alpha, it's angular acceleration. By the way, that also applies to rigid objects only. There's no such thing as a motion, as a rotational inertia or moment of inertia for a non-rigid object. Or you could, I guess you could define one at one particular moment, but it's going to be changing as the thing moves around. So the torque is equal to I times alpha. I is the moment of inertia or rotational inertia. It's a measure of how hard it is to rotate an object, how hard it is to get the thing rotating, not because of friction, but because of its actual intrinsic inertia. It depends, of course, on the mass of the object. The heavier it is, the harder it is to start it rotating. But also, and much more subtle, it depends on where that mass is distributed. If the mass is located far from the axle, then it contributes much more to the moment of inertia. It's harder to rotate an object that has mass out at the wings compared to mass riding close to the axis. The actual formula for moment of inertia is the sum over all the masses that go to make the thing up, mi, the mass of that thing, times the square of the distance from the axis. If the object is continuously distributed mass instead of discrete mass points, then this becomes an integral, r squared dr. My subject for today is the calculation of moments of inertia. I'm going to calculate the moment of inertia of literally, I think, 9 different objects to show you how to do it. Actually, the techniques techniques of calculation are not really what's important, so important to me. I want by the end of the class today that you would have a good sense of what the moment of inertia really is, derived from a string of examples. So, example 1. I have an object that consists of 4 masses located at the corners of a square, a square of side S, and each corner has a mass m on it. And I want to know what is the moment of inertia about this axis here. It's handy to put arrows on the 2 ends of an axle, so that the reader knows what we're spinning this thing around. So you got a picture, a frame, a square frame, 4 masses connected by very light rods. I'm not worried about those. And I'm going to spin this thing about an axis to the center like that. What's its moment of inertia? Well, I have to take the 4 objects there. Here's one of them, and add m times r squared, where r is the distance from the axis, for each one. So it would be m times, what's the r for the first one? S over 2. And then there's this one down here, m, likewise s over 2. Now there's this one. Uh-oh, it's over on the other side. What should I put in? S over 2. Somebody says, no, shouldn't that be minus s over 2, or shouldn't it be maybe a minus sign here? No, this is the distance from the axis. That r is the distance from the axis. I don't care if it's on the left or the right or sticking straight out. All I care about is what the distance from the axis is. In this sense, it's rather unlike calculating center of mass. It's easy to confuse the two calculations. When I'm doing center of mass, for instance, the x component of the center of mass is x dm. It looks kind of like this, but this is x. X can be positive or negative, this distance along in the x direction. R, and more particularly r squared, is always positive. But r itself is always positive because it is, by definition, is the distance from the axis, and a distance is always a positive number. So there's no opportunity for cancellations when you're calculating moment of inertia. Plus m times the last one, I don't know whether that's this one or this one, again it's s over 2 quantity squared. There are 4 of these, 4m s squared over 4. It just so happens that in this case the answer is ms squared. So far, so good. Moment of inertia depends entirely on the axis you're rotating about. So as I go along, I'm going to make comments here. How come? Because r is, by definition, is the distance from the axis. So suppose that I took exactly that same configuration of 4 masses. But this time, I propose to rotate not about the axis through the center, but an axis over here. I could do that, huh? Now I've got the frame there, and it's like a window on the hinges or so, and it's flipping around like that. What's the moment of inertia now? M, S, S, same dimensions. In fact, the same object, I'm just spinning it about an axis here instead of an axis through the center. So what do I get this time? Example 2. Well, I've got 4 masses. Let's start here. I equals m times, well, that's right on the axis. R is 0. This one, m times s squared, is all the way on s. This one here, again, ms squared. And the last one, 0. It's right on the axis. So I get ms squared plus ms squared, 2ms squared. So there's a moral in this story. If I show you an object and say, what's its moment of inertia? The correct answer is, moment of inertia about what axis? I can't tell you what the moment of inertia of this thing is until you tell me what axis you have in mind. And by the way, it doesn't even have to be an axis in the plane. I could be spinning this thing around like this, about that axis, or I could be spinning it around like this, about that axis. So the moment of inertia about every axis that you care to think of. So if somebody says, what is the moment of inertia of this axis? I can't answer the question. I can answer the question only with respect to a given axis.
Does the axis have to go through the object?
Have to go through the what?
Like the object, could it be rotated
No.
around something?
A good question, as a matter of fact. This whole thing, Frank, could have been way out here on some kind of long wires or so that was suspending it out here, and I could be rotating it around in a huge circle. That would be perfectly fine. But whatever the axis is, the distance in question, the r in question, is the distance from that axis. Let's do that same one. I'm going to squeeze a little bit more juice out of this one. Do it about an axis through this point here, but coming out of the board. Let's see if I can draw that. So my axis now I have in mind is one that would go in and out of the board, perpendicular to the board there and passing through that corner. Can you picture that? So this is the square, unfortunately, but it would be like an axis about this corner, and I'm rotating the thing around like that. Axis perpendicular. Perpendicular to the plane and through one corner. In that case, what is the moment of inertia? Let's see. This one here is right on the axis. This one up here is a distance s away. This one over here, whoops, how far away is that from the axis? It's diagonally opposite corner over here. What would you say?
That's square root of 2.
Root 2 times s, right? Because s is the square root of s squared plus s squared, which is square root of 2s squared using Pythagorean theorem. So this is root 2 s quantity squared for that one. And finally, I got the one down there, which is just a distance s away again, so ms squared. Now, what do I get all told? ms squared plus, squaring this out, 2ms squared plus ms squared is 4ms squared. So from the same object, I've got ms squared about one axis, 2ms squared about a second axis, 4ms squared about a third axis. So, depends a lot. Depends entirely on the axis you're rotating about. Okay, how about some examples of continuously distributed mass? Example 4 was the simplest continuous distribution of mass you can imagine. I suppose a stick, a meter stick, let's say, or in general, a nice uniform thin rod like this. Let's stick it along the x-axis, and I want to know about the moment of inertia of that thing about an axis perpendicular to one end. So let's give this a length L and a mass M. So about an axis through one end and perpendicular. what would the moment of inertia of that object be? Well, the general formula is the integral of r squared dm. In the same spirit that I did for calculating center of mass, I think I chopped this into a little segment here, a little section of length out at a distance x and of length dx. And now I want to know what is the mass of that little segment. dm, I'm going to introduce some handy notation. You don't have to use this if you don't want to, but it's handy for problems like this. Let's call lambda the mass per unit length. Pretty standard notation for mass per unit length, mass density along the line. What is that in this case, by the way? If the total mass was capital M and the total length is L, then the mass per unit length would be the total mass over the total length, assuming that it's nice and uniformly distributed along the So lambda is a shorthand for total mass over total length, but it's a handy shorthand. Okay, what was the mass of that little segment of length dx then, in terms of lambda? Mass per unit length times length. Make sense? You're quiet, and that always makes me nervous. Are you following this okay?
Yeah.
Okay, good. R squared dm. In this case, r, the distance from the axis, is nothing but x. So this is x squared times dm, the mass of that little hunk, which is lambda times dx. Now I've got this set up as an integral. Well, lambda, of course, comes out in front of the integral, and I've got x squared dx, and I want to integrate that between the limits 0, the beginning, and L when I get out to the end. So what does this give me? Lambda, the integral of x squared is x cubed over 3. So it's 1/3 x cubed. Evaluated the limits 0 and L. At the lower limit, 0 cubed, I get nothing. At the upper limit, I get L cubed. So this is lambda times L cubed over 3. This is a lousy way to leave the answer, however, because the reader was only told the stick has length L and mass M. Those are the variables we're supposed to give the answer in terms of. Along the way, it was handy for us to introduce the shorthand, lambda equals M over L, but at the end of the game, I should get that out of there. So let's put in M over L for lambda times L cubed over 3 is 1/3 M L squared. A famous formula, the moment of inertia of a uniform rod about one end, 1/3 ml squared. Is that a little bit weird? If I had had all of the mass out at the end here, it would have been ml squared. If I had shoved all the mass down to this end, it would have been 0. So evidently this is somewhere between 0 and ml squared. It turns out that it's 1/3 ml squared. Not like center of mass. The center of mass, of course, would be at 1/2 L. But moment of inertia, 1/3 ml squared. By the way, all of the standard objects, like a uniform rod about one end, or a uniform rod about the center, or a sphere about the center, or a spherical shell about a diameter, and so on. All of those are collected in the book. Nobody wants to recalculate the standard moments of inertia every time you hit a problem in rotational mechanics. So somewhere or other in every book, there's a little table that gives you a picture of all the standard objects and what their moment of inertia is, and then you never calculate them again. But once in your life, you should calculate it. Example 5. Hey, what's the moment of inertia of that stick about the center? In a little while, I'm going to show you a very quick and clever way to find the solution to this. But for this one, actually, there's another fairly quick way to do it. This is the same stick, so it's got the same length L and mass M. But this time, I want to know what's the moment of inertia about an axis through the center. So I got a meter stick here, and I'm spinning about an axis through the center this time. What is the moment of inertia about that point? I'll tell you, there are about 6 different ways that you can do this, but one cute way to think of it is that is nothing but 2 sticks about the end of each one, right? There's the stick on the right, this one here, and there's a stick on the left, that one there. So why don't I add up those 2 sticks using the formula up above? The only thing I have to be careful of is that, of course, the length of this stick is not L, but L over 2, and the mass of this stick is not M, but M over 2, right? So one way to do it is to think of it as 2 sticks. And then I quote the formula from up above. The total moment of inertia is going to be 1/3 the mass, but that's M over 2, times L squared, but L is L over 2 in this case. And there are 2 of them. So what do I get here? Those 2's cancel. I get 1/3 of M times L squared over 4. 4 3's are 12, and this is 1/12 M L squared. So there's the moment of inertia of a stick about the center of the stick. About one end is 1/3 M L squared. About the center, 1/12 M L squared. Hang on to that formula because later on I'm going to show you, as I say, a quickie way of getting the same thing. Let's see, we've done a stick now. How about a hoop? A hoop about an axis perpendicular to the center of it. So we're up to example 6, I guess. Here's the hoop. By hoop, I mean, of course, circular hoop, all the mass out of the rim, like a hula hoop or something like that. And I want to find the moment of inertia of that about an axle going right through the center and perpendicular to the whole thing. Let's give this thing a radius, R, and a mass, M. Folks, the hoop is the simplest case there is. On an exam, you should always hope that they ask you for something or other about hoops, because the hoop, the moment of inertia, is actually trivial. Isn't that right? Because every point on that hoop is out at the same distance from the origin, from the axis, namely R. So the moment of inertia of that hoop is nothing but mr squared. Does that make sense? By the way, it doesn't even have to be a whole hoop. It could be, you know, a quarter of a hoop or something like that, or some fraction of a hoop, as long as it's all out at the same distance, and this was supposed to be a very light rod there connecting the ends. As long as it's all out at the same distance, this moment of inertia is always going to be mr squared, or it could be just a bunch of points that are distributed around, a bunch of point masses distributed around on a bicycle wheel or something. The moment of inertia of that is trivial. It's the total mass times the square of the radius. But the hoop is the classic example. mr squared. Well, not much needed in that one. Let's go with this. So, uniform disk of total mass m, radius r. This time I'm going to be careful about what variables you're allowed to use in the answer. Mass m, radius r, and about an axis that's perpendicular, same as here. So here it is. But this time it's the whole plate, not just the rim. So the mass is uniformly distributed over the plate there. And I want to know the moment of inertia about this axle here. Like that. How should we do this one? I think the thing to do is chop it into rings. Think of it as nested hoops, if you will, going out from the center. We know what the moment of inertia of each ring is, so think of it as nested rings. I need to draw one of those rings. I'm going to look down on this from on top. Make it a little bit simpler. Looking down on it from on top, I chop it into rings. Here's a typical ring. It's out at radius, let's call it little r, and it has a thickness dr. And I would like to know, first of all, what's the moment of inertia just of that one ring. And then, of course, I'll add them up for all the rings that go to make this thing up. What is the sensible variable here? dm for that ring would be the mass of that ring, would be the mass per unit area now times the area of the ring. Just as lambda is the standard letter for mass per unit length, the standard letter for mass per unit area is the Greek letter sigma. And just as over here, you never had to introduce the lambda. You could have written everything in terms of m over L. It just makes your notation a little bit more cumbersome as you're going along the line, not to have that shorthand. Same story here. I don't need to introduce sigma as a separate thing, mass per unit area. What actually is the mass per unit area for this disk? Get that, guys. Total mass, right? Over pi r squared. Good. Over the total area. So it would be m, the total mass of the disk, over pi r squared. That's the mass per unit area. So the mass of this little ring, this hoop, is mass per unit area times the area. What would you say is the area of that hoop? The surface area of that hoop. Write that down. What's the circumference? 2 pi r, huh? And the thickness, if I imagine opening this out as a long ribbon here, the length would be 2 pi r, the circumference. The thickness is dr, so the area is nothing but 2 pi r dr. Did that make sense? Important point. Area of that ring is 2 pi r, the circumference, times dr, the width of it. So that's the mass of that one hoop here, and the moment of inertia of the whole disk then is equal to the sum or the integral of m, the mass of that one disk, the one hoop, which is sigma times 2 pi r dr. Times the square of the distance it is from the axis, r squared. Make sense? I'm using the formula for the moment of inertia of a hoop, plugging it in here with realizing that the mass of this particular hoop is sigma times 2 pi r dr. Okay, the sigma and 2 pi come out in front. And what I got for the integral is r squared, and another r there, r cubed dr. Limits on the integral? Well, I'm going to go from 0 all the way up to the full radius of the disk, so it's 0 up to r. Very well. Sigma times 2 pi, the integral of r cubed, r to the 4th over 4. So this would be r to the 4th over 4, evaluated at the limits 0 and capital R. At the lower limit, I'm not going to get anything. At the upper limit, I get capital R. So this is 2 pi sigma over 4, 2 pi sigma over 4 times r to the 4th. Is that an acceptable way to write the answer? I don't think so, because it's got my private notation in here, the sigma, for mass per unit area. I've got to substitute in the actual variables that were given. So what's that do? I is equal to, well, one of the 2's cancels. It's pi r to the 4th over 2. Pi r to the 4th over 2 times sigma, which itself is m over pi r squared. 2 of the r's cancel, and I get 1/2 m r squared. How about that? There's the moment of inertia of a disk. The same amount of mass distributed uniformly over a disk makes a moment of inertia that is smaller than a hoop. If you stuck it all out at the rim, you would have mr squared. If you smear it uniformly over the disk, 1/2 mr squared. Does that make sense? Yeah, mass contributes more to moment of inertia the further out it is. So the best you can possibly do is stick it all out at the very rim. Smear it out over the surface, you're going to get something less. In point of fact, you get exactly half as much. The fact that it's exactly 1/2 is not something you could guess from the outside. Actually, all of the problems that I got here are a mass times the length squared, right? Mass times length squared, mass times length squared, mass times length squared, multiplied by a different factor in each case. Of course it's going to be mass times length squared. What else could it be? Moment of inertia is an integral or sum of m times r squared. It's got to come out with the units mass times length squared. So whatever length there is in the problem, length of the rod, or the radius of the hoop or the disk or something, it's got to be of the form mr squared or ml squared. The only thing we're arguing about is what number goes in front. Make sense? Just by on dimensional grounds alone, you know that the answer has got to be mr squared times something or other. The only question is, what's the something or other? The numerical factor on the front. Okay, there's a disk. By the way, would it have mattered if this disk had been actually a uniform cylinder like that? I don't think so. Of course, that would mean that the mass is larger by however thick this thing is, but the distribution of the mass with respect to the axis would be exactly the same. I could think of it as a stack of pancakes, each one of which has a moment of inertia 1/2 mi times r squared, and I just add up all the mi's and I get the total mass of the whole thing. So this is also true for a cylinder. I've done a uniform cylinder about an axis about an axle along the axis of a cylinder. What number am I up to? 8. Okay, here goes the most famous one of all, the moment of inertia of a sphere about a diameter. sphere, let's give it a mass m and the radius r. By the way, sphere, I mean the solid sphere, right? Not a spherical shell. That would actually be a more complicated problem to calculate. I mean a solid sphere here. So whoops. Axle through the center, so this is like the Earth, and this is the axis of revolution of the Earth. The thing has a radius of r and a mass capital M, and I want to know what is the moment of inertia about that axis there. Well, I'll tell you what, why don't we play the same game that I suggested for the uniform cylinder there, chop this thing into pancakes. Here's a typical pancake on there. That's nothing but a disk, right? And I know the moment of inertia of a disk. What's the mass of this particular disk? Let's say that this is the z direction, and this thing has a thickness dz and a radius, I'll call it little r. What's the mass of that pancake? Well, now I need a letter for mass per unit volume, the density, mass density per unit volume. We always call that rho for some reason. Mass per unit volume, what is that in this particular case for this sphere? Well, it's the total mass divided by the total volume of a sphere. I didn't get a 3. It's 4/3 pi r cubed. Isn't that right? For the volume of a sphere, volume of a solid sphere would be 4/3 pi r cubed. Maybe you said it right. So total mass divided by the total volume, 4/3 pi r cubed being the volume of a sphere. So that's what rho is, the mass per unit volume. Now I come back to the question, what was the mass of my pancake here? This pancake with radius r and thickness dz. It would be mass per unit volume times the volume. What's the volume of that disk? Area times thickness, huh? So pi r squared times dz. Pi r squared for the area of the disk, the circular disk, and then dz for the thickness. So what's the moment of inertia then? It's the sum of the moments of inertia of all those disks. The moment of inertia of a single disk is 1/2 the mass of that disk, which in this instance is rho times pi r squared dz, times the radius of that disk, which in this instance is r squared, and now I'm supposed to add it up over all those disks. Well, some of this stuff is constant. Let's take it out in front. Pi times rho over 2, pi rho over 2. Now what remains is r to the 4th, d, not dr, that's dz. Oh my. I got two variables cooking under the integral sign. How can I integrate that? I need to know how r depends on z. Anybody spot the formula? We can get r in terms of, it is true that as you move up here, r actually gets smaller and smaller until it's finally 0 at the North Pole. It's the maximum, capital R, down at the equator, but the radius of those pancakes gets larger and smaller depending on what the value of z is. So if this is the pancake in question is I've got to find z. What is little r for that? Can you see the Pythagorean
R
theorem
squared
on this
is
triangle? Would say r squared plus z squared is equal to capital R squared. And therefore, little r squared is r squared, the co-radius, divided by, subtract by z squared. There it is. Now I substitute that in for the little r, and I got something I can actually integrate. Pi rho over 2 times the integral of r squared, r to the fourth, I'm sorry. So this thing, r squared minus z squared, quantity squared, because this is 2 of them, and I need to square that guy, times dz. What are the limits on that integral? I'm integrating over z, so what's the range of z?
From 0 to R.
Minus, no, not 0 to r, because it actually starts way down here,
Oh,
where z
minus.
was minus r.
Minus.
So it actually goes all the way from minus r up to plus r. Actually, it's pretty obvious that the contribution from the northern hemisphere is exactly the same as the contribution from the southern hemisphere. So realizing that, you could have integrated from 0 to r and then multiply the whole thing by 2.
Right.
That would do it also. Okay, how do I do this integral? Pi rho over 2. Integral, I think I better square this thing out. What's it give me? R to the fourth minus 2r squared z squared plus z to the fourth dz minus r plus r. Pi rho over 2. Okay, now, capital R is a constant. That's just the radius of the sphere. We're integrating over z. So what's the first integral? The capital R to the fourth just sits there, and I'm integrating dz.
Times Z.
Second term, the minus 2r squared is constant. I'm integrating z squared, dz. Z cubed over 3. Third term, I'm integrating z to the fourth dz, z to the fifth over 5. That's the whole integral, and I'm supposed to evaluate it at the limit minus r and plus r. Okay, now it's just a question of putting in for z, the value plus r at the top, pi rho over 2. So I'm going to put in z equals plus r. Here I would have a total of r to the fifth. Middle term, 2/3. If I put in z equals plus r, I got r cubed and another 2, so r to the fifth again. Plus, in this last term, r to the fifth over 5. That's when I put in the upper limit. Now subtract out the lower limit. I put in z equals minus r. I get minus r to the fifth. I've got minus from here, minus because it's the lower limit, because it becomes plus 2/3 times, now putting in z equals minus r, z cubed is minus r cubed, minus r to the fifth. And finally, minus, because it's the lower limit, z to the fifth, minus r, that's minus r to the fifth again, over 5. Notice that what happened here, this is another plus r to the fifth, This is another minus 2r to the fifth, and this is another plus 1/5 r to the fifth. So that's exactly what I was saying before, that you could have taken the whole thing and multiplied it by 2, and integrated just from 0 up to r. That would have done the same thing, because the lower limit is giving you exactly the same value as the upper one. Pi rho r to the fifth. What's the factor? 1 minus 2/3 plus 1/5. What's that add up to? I'm going to bring it to a common denominator, I guess, of 15. Then this would be 15 minus, you multiply top and bottom by 5, so it's minus 10 plus 3. 15, 16, 17, 18 minus 10 is 8 over 15. Weird factor here, but the answer is 8 over 15 times pi rho r to the fifth. Acceptable way to leave the answer? No, I ought to get rid of the rho there in favor of what I know it is. So this is 8/15 pi r to the fifth times rho, which was m over 4 pi r cubed times 1/3. The 3 comes up into the numerator. Tidy that up. A pi cancels. A 4 cancels into the 8, leaving me a 2. The 3 cancels into the 15, leaving me a 5. And 3 factors of r cancel, leaving me an r squared. Looks like the answer is 2/5 m r squared. That's the moment of inertia of the sphere. Now that we've calculated it, you never calculate that again until you're teaching a course in this subject. Then you have to do it once again. From now on, you simply look that up. But you know where it came from now. Actually, just calculating that integral for a moment of inertia.
But we could get something like this on a test.
To calculate that, I would not ask you to calculate that on a test yourself. I think it would be fair game in principle, but you try grading 80 papers when people are trying to do a calculation like that, and 2 people got it right. Not pleasant.